Thank you. So in this session, this is session 20, I think. The previous session we spoke about Euler's gamma function, and now we are going to speak about Riemann's zeta function. Which in fact, this function was already introduced by Euler himself. So many years before Riemann, and also he studied some of its properties, etc., and he computed some values, mainly of this function, okay? Riemann's zeta function, the usual definition is like this. Let us consider this is written like this, zeta of z as the sum from n equal 1 to infinity, 1 over n to the z. Okay, for the values where the sum converges. Okay, if you take any compact set contained in the plane real of z greater than 1, in this compact set the real part of k is bounded below by some number strictly greater than 1. So 1 over n to the z can be bounded by, this is 1 n real z, and this is, and of course this is a convergent series, so this defines a holomorphic function on this set, on this open set. Define a holomorphic function on the half plane of complex numbers of modulus greater than 1. Okay? You can recognize some values of this function. For instance, we have already spoken about Bassel's problem, which is to compute this value, gamma of 2, zeta of 2, sorry, and it would be pi square over 6. And in fact, Euler computed all the values zeta of 2n. Give a general method to compute all these values. And as I told the other day, the values for the odd natural numbers are not known. In fact, very few things are known about those values. So, this value, it is known that it is irrational, but few things are known about all these values. Okay, so the first objective will be, or one of the objectives of this session would be to relate the function zeta with the function gamma, and to continue, analytically continue this function z also to the whole complex plane, as we have done with the function gamma. First of all, we want to state some relation about the function gamma. So we want to find the formula for the product of gamma and zeta. We want to find a formula for this product. In order to find this formula, we are going to compute this expression, 1 over n zeta z times gamma of z. We want to compute this expression. This expression would be using the integral defining gamma function, something like this, and making the change of variables t equal to nu. We make this change of variables. We have here nz minus 1, uz minus 1. Here we have 1 over nz, e minus nu, and n ddu. We have another n here, so this goes, okay, and we have okay. And now we are going to try to compute this sum. we try to compute this sum. The sum would be this sum here. Equal to 1 to infinity. We will try to compute this sum, okay? So if we, in fact, we want to show that we can exchange the integral and the sum. So our objective would be to show that this is equal to the integral from 0 to infinity of this sum that could be one to infinity, and this is of e minus u, 1 minus e minus u, something like this. Okay, let me see if this is correct. There's something. Sorry, let me verify that all this is correct. Okay, and the u. So we are going to write this differently. Yes, this is correct. As u z minus 1, the u between multiply and divide by e to the u, u minus 1. Okay. So in order to see that this is legal, to make this exchanging of sum of integral as integral, first of all we will see that we have there an integrable function. Okay, we are going to verify that this function is integrable u to the function t. I return to the variable t to the z minus 1 over e t minus 1. We are going to see that this is integrable in 0 infinity. I want to see that. Okay, to see what happens at infinity, we could, for instance, multiply and divide by t here, so we have something as to see what happens at infinity. And if let us verify. Sorry, I'm a bit no, it's not the correct. No, it's not. No, this is good. This would be good for 0. Okay, in order to verify what happens at 0, let us compute, let us multiply and divide by t, okay? And when t equals to 0, this tends to 1. So it is bounded here, so this would be integrable at 0 if real of z minus 2 is greater than minus 1, so real of z is greater than 1. Okay, so this is integrable when at 0, at least. And to see what happens at infinity, okay, it's not so complicated. We could do like this. Okay, tz minus 1 multiply. We can multiply by t to the 2, for instance, and divide. Okay, and when t tends to infinity, is the same case. This tends to 0. When t tends to infinity, and this is integrable. So this is bounded, this is integrable. Okay, so finally, the function here, this function is integrable in 0 infinity. So first of all, this is integrable. So we have here a sequence of functions that the series converges to an integrable function. And this sequence of functions is increasing, at least if you take the absolute values of this function here, tz minus 1, well, these are positives, okay? So t real z minus 1 e to the minus n t, okay? You take this series, of course. This series is, of course, a series of positive functions. We have taken the modulus. So, of course, the partial sums of the series define an increasing sequence of functions. So we have an increasing sequence of functions converging to an integrable function. Using a dominated convergence theorem, we know that the integral of the limit is the limit of the integrals here. Okay, so again, using that result, we have shown that this sum, in fact, converges to this sum. And this sum here is precisely the product of zeta and gamma. So we have arrived to the following formula, that for values of z greater than 1, we have that zeta of z times gamma z is equal to the integral from 0 to infinity of t z minus 1 okay, we have this formula here. Okay, that's going to be quite interesting. This formula will allow us to continue the function zeta. How? So we're integrating along this half line here. Okay, and okay, we have at infinity we don't have many problems because okay, it's not quite hard. Here we can multiply. We have, in fact, we haven't used at infinity. You haven't used here that z is of real part greater than 1 or not. Okay, so we only had used that at 0. So the problem normally to extend to continue analytically is at 0. So a certain trick that is sometimes used is the following. Let us consider a different integral here. Let us change the path of integration and consider the integral along this path. Come here through this line, okay, take a small tour at 0 and return again to infinity. I'm going to design separately here a little bit. So here you have a path, a small circle of radius epsilon here. Epsilon, you can take some epsilon small enough such that epsilon is smaller than 2 pi. Why 2 pi? Because we don't want that the denominator can be 0 on this circle. So the denominator could be 0 for this integral when t is equal to pi I. So we take some epsilon smaller than 2 pi. Of course, it is 0 also when t equal to 0, but if you take epsilon small enough, it does not go through any point where the denominator is 0. Okay, you take this path, call it gamma epsilon, this path here, and consider the following function, h of epsilon of z equal to the integral along this path of this function. So we have a problem here with the numerator, because this is a multi-valued function. What is the numerator? The numerator is the exponential of z minus 1 log of t. And we have a problem here with log of t. Okay? So we need to find some logarithm that is, which is continuous along the path. For that, we could consider the determination of the logarithm defined here. Remove the positive real axis here and consider the rest. Okay? And take the determination of the logarithm where the argument is, in this case, between 0 and 2 pi. Okay? So you can imagine in this, if you can extend continuously, you can imagine that when you come here, the argument of these points is 0. Now you make a turn here, and when you come back, you don't come back exactly by the same with the same function. You come back with the function where the argument now is 2 pi. Okay? But normally the problem is going to be more or less in this part. Let us consider the circle here. C epsilon. This would be almost a circle of radius epsilon. Let us compute this integral, or let us try to bound this integral along this circle. So we have something like this. No, sorry, no, not for the moment. I need to make some another arrangements. We need to bound this integral. Okay, so see, this is the circle epsilon e to the I theta. where theta goes from 0 to 2 pi, essentially. Okay, so we have here, we can bound by, this is e to the z minus 1 log of t, e to the z minus, let's write like this, the modulus exponential of z minus 1 log of t would be log of epsilon plus I theta, something like this, and here must be the modulus and e theta minus 1, et minus 1. Okay, these bounds make me crazy always, but I hope not to e of t. Okay, I will change the blackboard to continue with the bounds here. Okay, so we can bound this integral the following way. Okay, et minus 1 in the denominator, let's multiply also and divide by t. So we are going to bound this by some expression like this. Divide by t, 1 over t, t would be of modulus epsilon. Okay, consider like this. This exponential would be, the modulus of the exponential would be the exponential of the real part. The exponential of this real part would be the exponential of the real part of z minus 1 log of epsilon. So epsilon to the real part of z minus 1 times the imaginary parts would be something exponential. Let's say the imaginary part here would be the imaginary part of z minus 1 times z. Okay. Let me see, the exponential of the real, modulus of the exponential of the real part, and the imaginary part is something like this. So, okay. I think it must be something like this. Imaginary of z minus 1. Okay, I'm not sure if I haven't made some mistake. So this 2 pi epsilon we must have here. Okay, and there is something that I'm not so comfortable enough. Okay, epsilon. Okay, there is something. I think this minus 1 can be eliminated because we have there something of modulus 1. Epsilon of z minus 1 times I theta. Epsilon minus 1 of I theta in modulus would be 1. So we have something like this. And we could bound at the origin. When we approach the origin, this is bounded in the neighborhood of the origin because when epsilon tends to 0, when modulus of t tends to 0, this tends to 1. Okay, we have some epsilon here, and well, this is epsilon, real part of z minus 1, and here we can bound this by epsilon 2 pi, something like this. However, there are some things that need to be fixed. What is important is when real part of z is greater than 1, this tends to 0. Okay, perhaps there is some bounds that are not too correctly done, but we have arrived to the good conclusion. Real part of this integral tends to 0 when epsilon tends to 0. So when we do epsilon as small as you want, this small integral is going to tend to 0. So when epsilon tends to 0, what do we have? We have the integral along the real line and the integral along again the real line, but after making a complete turn here. So this integral h epsilon of z is going to tend Well, in fact, this integral is independent of epsilon. You can see that the points where it is defined is independent of epsilon, and it coincides with the limit, and the limit of these integrals h epsilon when epsilon tends to 0 is going to be I moved too much. This integral when epsilon tends to 0, the limit is going to be the following one. First of all, we are going to have, first of all, this integral here, but in the opposite sense. So this integral from 0 to infinity of z minus 1, but in the opposite sense, the integrals before, we make this term, and we have the second integral here, but in the second integral, the argument has increased to pi. So in the numerator we have epsilon z minus 1 argument of t, z minus 1 log of t, sorry, log of t plus log of t plus 2 pi I. So we have the previous integral multiplied by e to the pi 2 pi I z minus 1. This is the same as this integral here. So we have this integral plus this integral also. Okay, so we know that the function h of epsilon z, when epsilon is small enough, all these functions coincide. In fact, we are going to call it h of epsilon, h of z, sorry. This is going to be times this integral. This is the value of this integral. Why is this important? Okay, the function h of epsilon, as it is defined here, is entire. H of z, sorry, or h of z or h epsilon z is an entire function. Why it is entire? Because we have avoided the bad point. Let's say we have a bad point at 0. At 0 we had the main problem for the function to be entire, for the integral to define an entire function, and we have avoided this point. So now the part at infinity is not a problem for us, it's entire, so this is an entire function. So this expression, hz, is an entire function that agrees with this expression here, and this is, in fact, this is when z has real part greater than 1. Z has real part greater than 1. Okay? So we have arrived to the following expression. Delta of z, zeta of z is equal to this function h of z quotient by can write like this. Okay, if we write like this, the expression on the right is a meromorphic function, because this is entire. Well, okay, these are entire functions. 1 over gamma is an entire function. Recall, 1 over gamma is well defined over the whole complex plane. So this is an entire function, a meromorphic function. So finally, we have that this meromorphic function agrees with the zeta. Riemann zeta function when real part of z is greater than 1, so this formula defines an analytic continuation of the Riemann zeta function to the whole complex plane. This analytic continuation may have perhaps some poles. Where it may have some poles? Okay, well, h is entire. H is entire. So, and 1 over z is entire. So we have h of z, 1 over gamma z here, and 1 over e to pi I z minus 1. We have this. This is entire, so the only poles may come from this expression. The only poles may be the points where this expression is 0, so natural numbers, integer numbers, sorry. Integer numbers are the only possible poles and such a function may have. Well, for the positive values, for the positive integer numbers, we already know that this function has no poles. I mean, if z is a natural number greater or equal than 2, no pole here. The function is well defined here. So the problem could be in 1, 0, etc. What happens in the points 0, -1, -2, etc.? In these points, this function here has a pole of order 1, and 1 over gamma has a 0 of order 1. So the order of the pole and order of the 0 here cancels, and this is a removable singularity. So this function h, this zeta function, can be extended also, and the points 0, -1, -2, etc. have no problem. So the only possible pole of this function would be the point 1, the point z equal to 1. Is the only possible pole that the Riemann zeta function may have. And in fact, at this point, it has a pole. It has a pole. Let us compute this. Pole. In order to compute this pole, the residue of this pole, let us compute the value of the function h at 1. The function of the value h at 1. The function of the value h at 1 can be very easily computed, because h at 1 would be, well, the value h epsilon at 1 for some small epsilon, and it is the integral of some epsilon like this of t to the z minus 1, so 1, would be this integral. But this integral is, we come here, we come back here. We don't have the problem of multivaluedness in the numerator here. So the integral along this half line at the beginning and the second half line are exactly the same. So they cancel. So in fact this integral would be the integral along this circle, along this small circle. And this integral along this small circle could be computed using residue theorem. So this would be 2 pi I times the residue of the function at 1. At 0. And this residue can be easily seen to have the value 1. So this integral is 2 pi I. So h of 1 is 2 pi I. And so now we have what happens, consider this expression, h of z, and gamma of z. We're going to figure out which is the value of this expression at 1, at the point 1. So we're going to see that, in fact, this has a simple pole. This expression defines a homomorphic function with a simple pole at 1. So we multiply this expression by z minus 1. Z minus 1. Z minus 1, and you take the limit when z tends to 1. So first of all, you consider this term here, and when you take the limit when z tends to 1, so you have z minus 1. So you have a indetermination, 0, 0. You could apply even L'Hopital's rule, and you would have to compute something as the limit of this expression. When z tends to 1, and this limit is 1 over 2 pi I. So this limit here is 1 over 2 pi I. The value h1 is 2 pi I. And 1 over gamma 1 is 1. So this limit is 1. So we have obtained that, in fact, Yes, this function has a simple pole at 1 with residue 1. So the Riemann zeta function is a meromorphic function having only one pole at z equal to 1, such that the residue at this pole is 1. Okay, but it's defined elsewhere, in any other point. Okay. There are some interesting formulas related with Riemann zeta function, and I want to give an idea at least of a proof of one of the formula that relates some values of that allows us to compute values of this function. Okay. So recall we have used some integral like this. We have defined some function h epsilon or h using an integral like this. Okay, we're going to define another function using another integral. We are going to use an integral as a path like this. Be a square like this, and we come back. When we arrive here to the point, something as 2m plus 1 times pi, if I'm sure, yes, 2m plus 1 times pi, it is a square, so the same length here than here, so this is the point 1 plus I. We're going to consider this big path, Cn, and to consider En, the integral along this big path, okay, of z minus 1. Consider the integral along this big path. And we're going to compute what is the difference among this integral En and the function h En of z. This is and the function h of z we have just defined. The reason for taking this value here is again to avoid the zeros of the denominator. The zeros are the points 2k pi I. So, well, I take the odd numbers here, and so you avoid these zeros of the denominator. Okay, this difference would be, let us make some drawing. The integral In, you come here and you make a big turn here. Okay, so let us compute this difference. So first of all, we have to integrate along this big square, and after that you have to remove the integral. The hz is the integral along the other path. So we are going to follow the other path, the path gamma epsilon, but on the opposite sense. So we come again by here, you make the turn here, and you come back here in the opposite sense. And some of the paths cancel. The integrals here is going to cancel, the integral here is going to cancel. So finally, in order to compute this integral, this difference, we have to compute something as the integral along a path like this. A square, we come back, something like this. Okay, and this integral can be, let's say, quite easily computed. We have a determination avoiding this half line, and we can easily compute using residue theorem, only having taken into account which are the poles of this integrand here. The poles of this integrand are on the points 2 pi I k, where k is an integer number, and we are going to take k from 1 to n, and from minus 1 to minus n. So the poles must be in the points 2k pi a, where k equal okay, so we need to compute the residues of those poles, and to compute the residues of those poles is no complicated. In fact, we have the residue of this function, the residue of the function here, of the poles here on the upper floor, let's say, on the positive imaginary axis, so it must be something like 2k pi to the z minus 1. This is a real number, so a positive real number, so no problem with the determination here of the logarithm, times exponential of I pi over 2 z minus 1. And let us observe that in the points on the negative imaginary axis, something has changed. Here we have that the argument is pi over 2, and here the argument is 3 pi over 2. So something here has changed. So the residue of this function at the points minus 2k pi I is going to be 2k pi to the z minus 1 exponential of e3 pi over 2 z minus 1. Okay? It's going to be that. So that integral over there, this difference of integrals here can be computed. This difference of integrals in z minus h of z can be computed as 2 pi I times the sums of the residues. 2 pi I times of the residues, something as, well, the sum of those residues, it could be the sum from k equal 1 to n of 2k pi z minus 1, this exponential, I pi over 2 z minus 1 plus exponential I 3 pi over 2 z minus 1. It must be something like this. Or in fact, from here, you know, you can make some computations and you arrive to the conclusion that this is In of z minus 2 pi I exponential of I pi z minus 1 sum of 2 times the cosinus. From this expression here you remove some term like this and you have some cosinus. You remember that the cosinus is exponential to iz plus exponential of minus iz divided by 2. Okay, so you can take outside the term like this in order to have the opposite terms inside the exponentials here and to write it as a cosinus. So you have 2 times a cosinus of pi over 2 z minus 1 and finally times the sum of k equal 1 to n of 2k pi z minus 1. Z minus 1. Okay? Something like this. Okay. We have this formula. Now, as usual, we can make n tend to infinity. N tend to infinity. So we have to bound this integral along on this the border of this big square, and you can do that when the real part of z is smaller than 0. When the real part of z is smaller than 0, you can see easily that, well, the denominator, there is no much problem with that, so it can be bound easily. 1 over et minus 1 is quite easy to bound either in the horizontal or in the vertical sides. It's not quite difficult, but the numerator is, in order to guarantee that the integral is going to tend to 0, we need that the real part of z is smaller than 0. So we have something that t to some real number of smaller than -1, and after multiplying by the length of the square, we still have something as let's say to a negative power, that some n to some negative power that is going to tend to 0, something like this. So when real part of z tends to 0, is smaller than 0, this integral here, this term in tends to 0, and we arrive to this expression h of z would be minus 2 pi I times pi z minus 1. Well, this is e pi z, e pi minus 1, this is minus 1. With this minus would be plus, so you can write like this. To here, cosinus. And what do we have here? 2 pi to the z minus 1, with a 2 pi here is going to be 2 pi to the z, and we have the sum from k equal 1 to infinity of k to z minus 1, and the sum is the value of the zeta function in the of 1 minus z, provided that the real part of z is smaller than 0. So, as we already know that this h of z is e to the pi I z minus 1 times we arrive to a, let's say, quite complicated formula, but I'm not going to write down all the details. If you make some computation in this formula, you can arrive to this simple expression, to this very, very simple expression. You can, which is a good relation about different values of the function zeta. You can arrive to the following expression. If you consider a function defined like this, xi of z, defined as zeta of z times gamma of z over 2 quotient pi to the z over 2, it turns out that xi of z this function here is symmetric with respect to this axis. The real part of z equal to 1. Well, this comes from this formula, well, after many computations, in fact. Many computations which involve, for instance, the complement formula for gamma function, okay, and the formula relating the values of z of the gamma function with the values of z over 2. So we need to work a little bit, and so you obtain this formula. Okay, valid. This formula would be valid in for some, let's say, some numbers, some complex numbers, but of course, by the identity principle, is valid everywhere. And this formula is used, for instance, to compute some values of the zeta function. For instance, let us compute, let's say, the value zeta of minus 1. Zeta of minus 1. So, in this identity here, we replace zeta by minus 1. If we replace zeta by minus 1, you have zeta of minus 1, gamma of minus 1 over 2, pi of minus 1 over 2 equal to this formula with 1 minus zeta. So, zeta of 1 minus minus 1, zeta of 2, gamma 1 minus zeta over 2 would be gamma of 1, and here pi 1 minus zeta over 2 would be pi. Okay, which values here do we know? Gamma of minus 1 over 2. We know that gamma of 1 over 2 is pi to 1/2. Okay, but gamma of 1 over 2 is minus 1 over 2 gamma of minus 1 over 2. So gamma of minus 1 over 2 is minus 2 times pi 1 over 2. We have here that. More. Zeta of 2. Of course, this is our value, pi square over 6. And so we have pi minus 1 over 2. We have here a pi 1 over 2. Okay, so we have pi and the numerator, pi and yes, and here we have also pi. So all the pi's disappear. Gamma of 1, of course, is equal to 1. So what we have finally is minus 2 zeta of minus 1 is 1 over 6. Okay, so zeta of minus 1 is minus 1 over 12. It's a curious value. That, for instance, Ramanujan obtained using completely different methods. So this value can be, in a very funny way, written like this, because this is the value of zeta of minus 1. So if we take the expression of the function zeta as 1 over n to the z, when we put here a minus 1, we obtain here the sum of the natural numbers. So we could say something like etc. We say that the sum is minus 1 over 12. In some sense, it could be correct. Okay? Even in more senses that it's not. It could be correct, this expression. Anyway, the value of zeta of minus 1 is this value here. Anyway, this formula, this is quite a very interesting functional equation that relates the zeta function with the gamma function. Of course, I haven't done all the details because, well, there are many computations here that are quite crazy sometimes, but most of them are not easily, are not too difficult. It's only a question of, let's say, have to have some time to make all bounds, etc., write down precisely the bounds, and not to make mistakes writing these bounds, and I always make mistakes with these bounds, so I prefer only give the final results of this. Okay, so these are more or less the main properties of the gamma and zeta function we will need. In fact, less than these properties. I will not need all these properties, but some of them I will need. And in the next session, we will begin to use the zeta function to study prime numbers. So how can we relate zeta function with prime numbers? And from zeta function, how can we deduce what is called the prime number theorem? A theorem which says asymptotically how many primes are there, essentially. And I stop here. Thank you.